Okay, let's start. Good afternoon, everyone. This is Yi from National University of Singapore. Unfortunately, the author of this paper are unable to come to the conference, so I'm here to represent them to present the work on high-resolution millimeter wave imaging using Metasurface and Diffusion. And this work is under the collaboration of MobiSys Lab of Shanghai Jiao University and Microsoft Research Asia. With the fast development of commercial millimeter wave radars, sensing using millimeter wave has become a hot topic in various applications. It has the advantages in inherent high range resolution because of the short wavelengths, the ability to penetrate through non-metallic materials, and non-ionizing property, making it well suited for human-involved sensing applications. With the rising need for fine-grained imaging in obstructed or privacy-preserving conditions, millimeter wave imaging has become popular in security checks, package inspections, gesture capturing and fall detection, and autonomous driving and object detections. So the millimeter wave imaging is promising for occluded or privacy-preserving scenarios. Previous solutions for fine-grained millimeter wave imaging include the point cloud-based approaches while beamforming scanning, the star approaches static object imaging, and the inverse star approaches for moving objects with non-motion states. However, the fine-grained beamforming requires a large antenna array, which is bulky and expensive for everyday scenarios. SAR requires the mechanical scanning, which is time-consuming, and the inverse SAR is unable to image static or random moving objects without external speed monitors. Therefore, a cheap, compact, stationary millimeter wave imaging system that can image arbitrary objects is a great need. One solution to achieve stationary millimeter wave imaging is computational imaging. Generally, the signals emitted by the transmitters propagate to the target object and reflect back to the receivers. If we decompose the target objects into pixels, then the received signal is the superposition of signals reflected from each existing pixels. Therefore, the imaging reconstruction problem is to determine which pixels contribute to the received signal, forming an optimization problem of solving image X from R equal to AX plus N, where A is the complex measurement matrix of all signal channels. In order to solve X, the measurements M should surpass the total pixels N. And in another word, the rank of A should surpass the total pixels of the image to retrieve the unique solution. However, taking abundant measurements is impractical in real-world applications. To reconstruct high-dimensional data with limited measurements and insufficient antenna arrays, the compressive sensing algorithms are applied to the wireless imaging problem, such as optimization-based algorithms like ADMM and message parsing algorithms like AMP. These methods suffer from suboptimality and require strict assumptions in images. However, real-world scenarios often impose challenges to compressive sensing. First, the insufficient antenna array limits the channel complexity, resulting in low rank A. And second, real-world objects do not always satisfy the sparse or low rank assumption, so it doesn't satisfy the needs of traditional compressive sensing methods. And third, the phases of signal channels undergo random channel drifting, making the measurement matrix changes over time. Let's first look into the problem of insufficient channel complexity. Take 5 points from an image plane for examples. The channel model for the target points can be modeled with a forward channel from transmitters to pixels, and a backward channel from pixels to receivers. Due to the simplicity of the signal channels, the signals from distinct points will be overwhelmed in noises and indistinguishable. This can be further observed with the correlation matrix of A, where a low rank A indicates indistinguishable neighboring channels. By enlarging the antenna array, the channel complexity, in other words, the S rank, can be increased. However, it's expensive and complicated to custom and expand the antenna array because of the extra expenses of semiconductors and customized manufacturers, and exponential increase in design complexity. Therefore, it's impractical to expand the physical antenna array beyond commercial mmWave radars. Therefore, we adopt a transmissive metasurface to expand the virtual phased array, therefore enhancing channel complexity and increasing its rank. As a result, the interclass spacing of different pixels are distanced and the signals are distinguishable. In order to fully exploit the phase manipulation ability of the metasurface, first, we need to design functional unit cells to work in the high frequencies of the mmWave radar from 77 GHz to 81 GHz. We need the unit cells to have penetration loss below -1.5 dB and near 2 pi phase control in the design frequency band. Together with careful unit cell geometry selection and the high-frequency response simulation via HFSS, our single-layer unit cells can support a transmission coefficient above -1.5 dB in our efficient working bandwidth and a phase modulation range of over 200 degrees. With the expanded virtual phase array, the channel complexity is increased significantly. However, traditional compressed sensing still fails to reconstruct high-resolution real-world images due to the impractical target structure assumptions. It is proven that the optimization-based compressive sensing, such as ADMM with lasso, is a suboptimal estimator of MSE loss. An optimal approach for MSE loss is approximate message parsing, which approximates the ground truth image from noises iteratively under the prior knowledge of the signal. A thresholding operator is applied to filter noises in each iteration. However, the form of the thresholding operator relies on strict data distribution assumptions, such as the sparsity. By observing the structure of optimal message parsing and the diffusion models, well, we noticed that the diffusion models share the same form of denoising approach with message parsing, while the signal prior is replaced with the transformer to embed signal knowledge, and the thresholding is approximated by a neural network such as UNet. In this work, we have proven that diffusion models are optimal estimations under MSE. Furthermore, by approximating the thresholding operator with deep learning models, the diffusion model inherently learns the characteristics of the images. Therefore, it's free from any explicit data structure assumptions. To this end, we develop a signal-to-image diffusion model to perform image reconstruction under the guidance of received signals. Our model composes of two parts. The first part is the signal embedding neural network named signal neural network. The received signals and the measurement matrix are served as inputs and are encoded and combined into signal embeddings to guide the image generation. The second part is the diffusion network named deep neural network. The diffusion process starts with a random noise image and denoises iteratively. The image representation are aligned with the signal embeddings to build connections between the image contents and the corresponding signals. As received signals and the measurement matrix are crucial in guiding the image generation process, the rank of the measurement matrix must be as high as possible. We use the metasurface to expand the virtual phase array. However, adding a random phase array is not enough to maximize its rank. Therefore, we adopt an end-to-end optimization to jointly optimize the phase pattern of the metasurface and the diffusion model to maximize its rank. As the transceivers and the predefined image plane are static, the measurement matrix A is determined by the metasurface phase map A and the transmit phase codewords. The measurement matrix and the diffusion model are optimized to minimize the MSE loss of the reconstructed image, alternately to achieve best reconstruction performance and maximize the channel complexity. Then, the optimized A and diffusion model are used for imaging process. The foregoing approaches can provide optimized image reconstruction under invariant channel conditions. However, for commercial mmWave radars, the phases of the channels often suffer from random drifting. For example, when we capture the reflection signals of the target right after obtaining a valid measurement matrix with channel calibration, the received signals and the measurement matrix are under the same channel condition. So it will result in good image performance. Due to the hardware imperfection and potential electromagnetic interferences, the channel condition is changed greatly over time, leading to misalignments between newly received signals and the old measurement matrix. As channel drifting causes the measurement matrix to be outdated, the recalibration process is required to update the measurement matrix. However, frequent calibrations are labor-intensive and time-consuming. Therefore, we need to find an efficient way to update the measurement matrix. Our efficient channel updating aims at solving the updated measurement matrix with a few non-image templates. Recall the mmWave imaging problem, where the received signals R, the measurement matrix A, and the noise N are known to solve the unknown image X. But for channel updating, we take a few measurements with non-image templates. Therefore, the image X are known instead of A. And now, A is the unknown to be solved. This is another compressive sensing problem. The real-world A is not low rank. However, we can estimate the rank distribution of A and describe it with a spectral profile P based on history measurements. The spectral profile P is then used as a regularization term to constrain the compressive sensing problem. Then we use ADMM to solve the compressive sensing problem and update the measurement matrix accordingly. To sum up, we propose the MIMSI to reconstruct high-resolution images, while a passive metasurface and a signal-to-image diffusion model. The metasurface is designed and optimized while end-to-end joint optimization to expand the virtual array and enrich channel information. The received signals are input into a signal-to-image diffusion network for super-resolution image reconstruction. We further adopt an efficient channel updating to resolve the frequent outdated measurement matrix caused by channel drifting. Our system prototype composes of a cascaded mmWave transceiver, a passive metasurface, and a 3D printed grid as the image plane. The mmWave transceiver contains 4 cascaded FMCW transceiver chips and has 12 transmitters and 16 receivers, forming a 192 channel virtual transceiver array. The passive metasurface is PCB printed and contains 80 times 80 unit cells in total. We evaluate the effectiveness of our imaging system by comparing 4 baseline setup schemes with or without the optimal metasurface and code words. Our approach with jointly optimized the code words and metasurface outperforms other schemes significantly, indicating the effectiveness of our metasurface in increasing channel complexity and improving imaging performance. When comparing with other imaging algorithms, our diffusion algorithm outperforms the lasso solved by ADMM and the traditional denoising diffusion model. Compared with mechanical scanning style approaches, our system is comparable to a star system with 20 centimeters times 20 centimeters aperture size and 192 times larger virtual antenna array. Our system can image all the shapes and types of objects and is capable of generating 3D images across different depths, indicating the robust performance of our system in real-world scenarios. That's all the presentation, and for more details on our work, please refer to the paper. And if you are interested in our work, please also check out the internship program at Microsoft Research Asia. The MSRA Wellness Group in Shanghai is always open for new interns and new ideas. And now I think the first answer of this work, Yida, is online. And welcome to have any questions. Thank you very much.
make sure that we can hear the...
Yeah, hello, Yida. Can you hear us?
Hello, hello. Can you hear me?
Hello?
Hi.
Hello, Yida.
Yes, yes. Can you hear me?
Yeah, I think they're coming. Can you double check that?
Setup? Oh, yeah, this one.
Hi.
Let me drag it. Yeah. Hello, Yida.
Hi.
Say
hi.
some words.
Okay, great.
Yeah, hello, hello everyone. Can you hear me?
Yes, we can hear you fine. Can you hear us?
Okay.
Yes, I'm guessing. Okay. Yeah, if you have any questions, feel free to use the microphones. I can start with a question. Great work, and we're sorry that you couldn't make it here. Did you actually, using the cascade radar, it's already pretty large antenna array. So I'm curious if you just switch to a radar with 4 antennas and just rely on Metasurface, would that be sufficient to get a good image?
You mean just using the cascaded radar?
No, instead of using the cascaded radar, use one of the other TI radars that only has 4 receiving antennas.
I'm
Let me
sorry if
phrase
there's
the
a...
questions. And Jiao is asking about what about using a radar of 4 transmitters, right?
4 receiving antennas, yeah.
4 transmitter array and 4 receiving antennas.
And plus the metasurface.
Yes.
Yes.
Yes, well, we have tried that setup before, but the small array of the radar does not satisfy our goal in achieving sub-centimeter resolution. So if we use the cascaded radar, the original resolution in the angles is merely 1 degree on the horizon direction and over 15 degrees on the vertical direction. And with our metasurface, we can increase the resolution to 0.1 degree in all directions. But if we use a smaller radar array in the beginning, then the potential of the system is highly reduced and is very hard to achieve our goal in achieving sub-centimeter resolution.
Cool. Yeah, thank you. Yeah, go ahead.
Thank you.
Hi, this is Yida from University of Washington. So my question is, have you tried directly input the raw signal of the cascade radar into a neural network? Let's say that it's like a diffusion network. So will that also get like a relative, like good performance?
Hi, Yida, do you hear the
Hi.
question?
There's echoes. Can you repeat the question?
Okay, I will rephrase the question. One audience is asking about, have you ever tried use the raw signal, right? You use the raw signal to a neural network instead of the diffusion diffusion model, and what's the performance of it?
No, I mean, using the just the physical array of the cascade radar to produce a low resolution image, and then input that low resolution image into a neural network, some kind of like super resolution network. Without the meta surface, can you get good performance?
Yeah, an end-to-end machine learning approach as opposed to relying on a signal processing plus Metasurface.
Yeah. I think he is asking about, hi, Yida, can you hear us?
Yes, yes.
I think he is asking about what about using the cascaded radar and to generate the low resolution image and just transfer it to super resolution neural network. So what's the comparison of your signal processing method with the Metasurface to that method? Yeah.
Because the signals we have received have many physical information of the target itself. If we capture the low resolution image and then transfer it into another super resolution neural network, there can be some losses of information in that process. And training such super resolution networks require a lot of data of one certain distribution, while our diffusion inherently learns the connection between the measurement matrix, the received signals, and the corresponding images. So the physical informations are not lost in our architecture. Yeah. So we have the potential to build higher resolution images. Thank you.
Cool. Yeah. Thank you.
Thank you.
Okay.
Great.
Thank you.
Let's
Thank you very
thank
much.
our speaker again. Yeah. Move on to the next presentation.